considering that, what I want to go over with you is some of the architectures and associated trade-offs, because most of those things are really overlooked. Then another thing is the inference time intelligence. Also, I think it's rather newer paradigms, therefore it's also often overlooked. And adaptive compute and learning efficiency, also more recent paradigms and also frameworks, and then system level optimization. So yeah, and it was already mentioned. So for all of you who want to go deeper into what I'm presenting during this talk, all of the topics will be covered in the books in more depth. Both of the books have or cover part of the topics I'm covering today. All right, so let me start off with AI agent economics. So really one thing you need to think about is that every token, every API call or reasoning step has really an economic signature, and the art here lies in deciding when and how to spend it. So given that, really context matters, not only for your information, for your model and your agents to perform better, but also for your costs. So costs are per step, not per request. And each reasoning step, of course, and tool call adds to the total. So yeah, this is just kind of an overview, what is all involved in that. So it's really about getting the bigger picture. So choosing the right architecture and thinking about that modern model variants specialize kind of the core for the target workloads. And the choice depends really on your objective, on the context flow, on serving constraints you have, and each architecture type serves a specific role in the overall modern systems. And the right fit combines your objective, the compute, and really your constraints. So, and for me, how I think about when I set up my agentic architectures, and I'm not just having one, I have several ones. So how I'm thinking about all those models I'm engaging, and I'm engaging different ones, is I'm taking a step back and I think about those models the same way as I hiring team members. So I think about what kind of skills they have to perform. I think about what kind of costs are associated for the team I want to establish. So this gives me a guideline in how I look on my overall agentic architecture. So what kind of skill set do I really need? And also boil it down to what do I expect from the models I involve or bring into that architecture. So that means, how do we get smarter, better, faster, and stronger? And how do we choose how do you choose your model? And yes, if someone recognizes this is a reference to the song from Daft Punk. It's also a title of one of my books. So this is a strong reference in how to think about models. So how do we get all that performance out of them? And yeah, so model selection matters. And here also not only the architecture, but also big versus small. So one size really does not fit all. And the choice of model impacts the performance and your costs. And think about that. Small models are ideal for routing. They are specialized for simple tasks, and they are fast and they are cheap. And you use large models for complex reasoning, planning, or deep research. And then, of course, the combination is important. So you use small models for the easy parts, and the large models only when hard problems are require that. And this, again, the reference to hiring a team or team members, you don't just hire all experts in your team. You have interns, you have entry-level jobs, and you have the senior experts in your team. So this is really the same. So then how do you actually choose the right architecture? So what I want to let you see here is you can think about what kind of things you need. So do you need bidirectional context at once? Then you have to choose the encoder. And do you need stepwise generation? Then you go for the decoder only. Do you need input to output mapping across domains? Then you go for encoded decoder. And of course, if you need capacity without linear compute growth, then you go for the mixture of expert models. And if you're thinking now, well, encoder and encoded decoder, aren't they outdated? Well, not quite. And I will show you some examples in the coming slides. And here, this slide and the following one, these are two tables. I won't talk about them. I just want to reference them for you so you have the slides for your resource to download, also for some links and hints I did put in to libraries to compute your costs and things like that. And I did put those also for you as a quick reference to go back to my presentation and have kind of a rule of thumb how you can think about setting up your models within your agentic system. So here's the same, that's a task mapping, again, as a rule of thumb and helper for you to think about how you set up your agents. So then if we go deeper and looking into decoder only, so what are the strengths of those? So the natural fit, they're a natural fit for open-ended generation and tools. They scale well with more data for instruction following. And the limits are the weak for global classification without adapters. So encoders are really better, not decoders for that task. And they are costly for document retrieval at scale. So every token counts. And another point I want to cover is really, and maybe not all of you think about this either, is thinking about key caching. So, and why does it matter? Well, basically it avoids recomputing keys and values for history. And why do we do that? So you might know that decoder only are also named autoregressive models. And autoregressive just means auto is self, and regressive means based on prior values. So this is actually what it's all about. Those models compute or have a next token based on the prior values. So the key values aren't changing. So we can reuse that for the generation for the next token. And this is where key caching in speeding it up. So we have a higher throughput win at the cost of the memory. So the memory, of course, grows with the sequence length, with the layers you have in your model, and with the heads you have in your model. And what are some of the deployment tips I can give you? So use cache reuse across beams if possible. Trim prefix, then context expands beyond the window. And this also, as a side note, you might have heard about this as well, this helps you actually in addressing to some extent the haystack problem. There, just the accuracy of your model decreases because the context window is too big. And of course, monitor cache hit ratio and memory pressure. And all of the things I mentioned right now with the deployment tips and the key cache and things like this, these things are all implemented already in the common frameworks. So TGI from Hugging Face gives you ways of handling that. VLLM, SGLang, all of those give you ways of managing the key cache and the memory. And VLLM even gives you a way of putting the memory out to CPU from GPU to expand the memory you have. You can actually swap the memory. So going over to encoder only models. So what's the task fit here? So we can use them really good for classification and tagging over full context. So dense retrieval, re-ranking, and they have low latency for batch inference over corpora. And like I mentioned, so they are not outdated. We have modern encoder-only options, modern BERT, NeoBERT. There are several ones. Actually, I cover those in my agent book in chapter 4 I'm currently writing. And there are similar ones for efficiency gains. And there are also distilled encoders for production serving. And also, just as a side note, to remember how up-to-date those models still are. So Meta has a suite for cybersecurity and for moderation called Purple Llama. And one of their models in that suite is based on a distilled BERT, which they further distilled. And this model has only 86 million parameters. And it's used for detecting malicious prompts. So just to give you another example, so encoders are really good for classification and are still in use, even older ones. So now thinking about if you're having RAG within your agentic setup, so encoder versus decoder, and how could you approach this possibly to save money? So encoders serve as retrievers to fetch context, and decoders consume the retrieved chunks to generate the answers. And of course, the separation improves efficiency and the quality, and of course, your cost as well. And some additional notes on serving and scaling, and this wasn't intended. So encoders batch well for high throughput, decoders need Kiwi cache and streaming optimization. And then if you're using mixture of experts models like Qwen3, well, they have dense and mix of experts combined in that release. But if you're using one of them, this adds routing overhead, and you should monitor and balance the metrics. And some of the common pitfalls I've seen is that there will be usage just of decoder only for pure retrieval jobs, ignoring memory costs of Kiwi cache at long context. And just to leave you with sort of a practical checklist before I'm kind of finishing up that part of the presentation. So before choosing your model, think about the objective, the data model, your latency and batch requirements, the memory and hardware limits. And before you're serving, think about your throughput profile, the cache policies, and the telemetry for routing and retrieval quality. So now let me go how we go from architecture to inference. So once we've picked the right model, then of course the next question is how much thinking is worth paying for? And I already mentioned test time compute. So we are here about to think smarter, not just, or be smarter, not just bigger. So smaller models really can outperform larger ones. Then you give them more time to think. And what you should do is you should evaluate different sampling strategies to give the agents more paths to explore to find a solution for your problem. And a very prominent or common method is Monte Carlo tree search for decision making. And you can also use best of N or beam search. These are also viable solutions and have shown that they have really good results. And to give you a bit more understanding what I mean with that and why does this matter. So here are two examples of like simple sampling strategies. So one part is we do repeated sampling, and this basically just means we explore. So we sample n amount of answers and get different ones. Then on the other hand, we could do sequential sampling, and I'm quite sure you've done this oftentimes before with any chat model, so questioning or asking it to provide further answers based on more input and refine it. So what you do with that is you exploit a single answer, so you go deeper with that. Now, if we look at tree-based algorithms like Monte Carlo tree search, what you do is you combine those two paradigms. So you exploit and you explore. And what you do with that adaptive branching, and this works actually quite good, you do this dynamically. So the decision will be done dynamically based on your provided feedback signal. So you can define your matrix, how you evaluate if you go wider or deeper, and this will be fed back into your algorithm, into your model, and will refine it appropriately. And I have a little bit earlier, I have linked to the library when I introduced it. And what you see here is a link to a repository from the prior talk. And I used there the adaptive branching for coding agents to iteratively improve over giving me a solution for the Fibonacci sequence. All right, so going to the part about reasoning. So reasoning smarter, not harder. And we have two thinking modes, right? So we have a thinking mode where we have a full chain of thought reasoning for complex problems. So we have higher costs, higher accuracy. And then we have the no thinking mode, which is concise, direct answers for every task. And we have lower costs and higher speed. So what you ideally want to do, you want to reason with dynamic control. So thinking versus non-thinking. And the good news is, if you not already know, that you can actually switch between the thinking and non-thinking mode. And many common frameworks provide this. But even if not, and I tested this and it actually worked surprisingly well, you can just tell the model to not use thinking in the prompt. And you see here with transformers, so with Hugging Face, TGI, with VLLM, they have a functionality that you can actually turn it off. And another thing you might want to consider, and this works again also fairly good, is introduce a thinking budget. So you still use the reasoning of the model, but now you constrain the reasoning of the model and how much it can reason. And then you can have it even fail or inform your user gracefully. So you see here, I have for early stopping text, I have that you could add your custom text for that failing of gracefully. And what the model does is it consolidates the prior thoughts and gives, based on that, gives the answer to you or to your user. So how do you decide the right amount of thinking budget? So avoid setting the thinking budget too low. Of course, this can limit really the model's reasoning ability. Adjust the model based on the value based on the latency tolerance you or your end users have. So this is really important, of course. And a thinking budget higher than 1024 typically provides really better overall performance and better handling of multi-step complex reasoning tasks. And again, to that thinking budget, I just want to have it as a side note that also VLLM provides you with a functionality, and even open source model provider for cloud provider like Novita AI or Nebius, you can set that thinking budget when you call the API. So this is really possible. This is a possible way for you to reduce your costs and also the latency when you're using thinking or reasoning models. And another way of approaching this, if you want to even go a step further and even fine-tune your models to behave differently or choose automatically based on the difficulty, there's also a way of doing adaptive compute allocation. And I linked the paper, Adapt Think, and basically it decides based on, or helps the model to decide based on the difficulty, be it easy or hard, to go into the thinking or no thinking mode. So basically what it does, it teaches the model then to think and then adapting the reasoning depth dynamically on the task difficulty. And this, of course, transforms the LLM from just a mere reactive responder to more of a strategic resource manager that allocates compute more intelligently. So you save with that, again, costs. And the core insight I want to leave you here with is that really chain of thought only improves the results for hard problems, not universally. So really adjust it and have only the thinking then it's appropriate for a harder task. And it gives also a specialized objective. So AdaptThink gives a specialized objective, which is a hyperparameter you can set, which penalizes the model for underperforming and rewards it for efficient, no-thinking decisions. So you can nudge your model even further in behaving more economically and saving you actually money. So now let me go from inference to learning. So there's a way of teaching your agents new skills and also better collaboration. And this makes them economically intelligent for your system. So there are two frameworks, and one is ART and one is Ruler. And ART is for reinforcement training framework for large language models, or better, for agents. And Ruler is a ranking framework which uses an LLM as judge to rank multiple trajectories. And this enables scalable, label-free, and consistent reward evaluation. And actually what it uses, or what kind of paradigm it adopted, is that decisions or evaluations and ranking are better done in group. So it adapts what was initially introduced by DeepSeek Math. So it uses GRPO, so the group references for the optimization, and even the newer one, which was introduced just recently for Qwen3, which is the group sequence optimization for the policy. So one is just on the token level and the other is on the whole sequence level. And you can use both to improve your models or improve better your agents for the tool usage. And this is for individual agents. Now, if you want to go even a step further in this whole setup, then you could go for RLLM. And they even recently introduced a new iteration. So it's about 2 or 3 weeks ago when they introduced it, or even 4 weeks, yeah, something about that. And what they made now possible is not only to train your individual agents and make them better and make it easier for you to use within that LM setup. It helps you to actually make your agents better behave in teams. So it really extends the reinforcement learning beyond individual models and trains the entire agentic workflow. So you can have planners, solvers, judge, executors, and help them to learn to collaborate and improve collectively. So within your multi-agent system. And what you have is a training workflow level learning. And this helps to orchestrate reasoning across those multiple agents. And you collect and optimize trajectories. So the whole sequence to find the solution, tool calls, all of that, from complex control flows and even search trees. So also the recent method I showed you with Monte Carlo tree search, and have this within your agentic setup, this framework even helps through improving that as well. So agents learn not only in isolation or not in isolation, but they learn to behave within a team. And they get shared rewards and trajectory aggregation. And this enables that solver judge or planner execution pairs to align their reasoning strategies within that whole system. And of course, this turns the real reasoning process into training loops, and it gives you continuous refinement for coordination, adaptability, and decision quality in production-grade multi-agent system. Because what you can do is actually you can record all those trajectories during deployment and then use this to make your agents better over time. So use the data you gather during your having them deployed and improve your system. Now, if you're training your models with reinforcement learning, there's also something you might want to think about in actually improving the overall spend on that. And there's where system level optimization for your LLM policy updates come in. And this is also just very recently released framework from Moonshot AI, and Moonshot AI are the authors of Kimi, K2, and other also multimodal models, recently published with fairly good accuracy and fairly good performance. And the recent one is not a reasoning model per se, but it has sort of reasoning capabilities. It is specifically trained for tool usage, and it's purely trained with reinforcement learning. And they decided to make the optimization they actually implemented to make this training of that model more efficient and less costly. They open sourced it into that library. And what it does is it solves that training bottleneck. So with the checkpoint engine, you accelerate the reinforcement learning by streamlining the transfer and the updated model weights between the learner and the training engine and the actor. And what you have is a co-located architecture. So both engines you need for the training run side by side on the chain, the same GPU workers, and this minimizes data transfer latency, enables high frequency RL loops, and in general optimizes your overall span and the time you need to train. And what you can do on top of that, you can introduce continuous learning in production, so you can have that updated policies kind of instantly distributed to actors, keeping the models deployed, fresh, and turning that reinforcement from research setup to a more scalable and real-time system. So, and I guess I'm running out of time. And let me leave you with some key takeaways I want to have you with. So it's really super important that you choose the right model architecture. Again, think about what I've said. It's kind of the same if you're hiring someone in your team. Think about your agents the same way and have thinking only when needed, route intelligently, train through feedback, not just data. So really use what you have. And again, the ruler, it's super simple. You just have to kind of do the same as you would frame a prompt, and it helps you introduce. And if you want to look for some code, go to my code repositories of the books. I have examples there for you to train and test out. And yeah, optimize your systems, not just models.